What's up, guys? It's me, Sir Ernest, and today we're going to talk about energy in relativity. Just like in the classical case, we need to start with a discussion of work done before we go to a discussion on energy. So let's recall classically that the net work done on a particle by a force F from point 1 to point 2 is given by the integral of F dot Tr from point 1 to point 2, and this is equal to T2 minus T1, where F is the force exerted on the particle, dr is the infinitesimal displacement made by the particle from point 1 to point 2. T1 and T2 are the kinetic energies of the particle at points 1 and points 2. And Newton's second law of motion is given by F equals the derivative of the momentum with respect to time. Relativistically, we define the linear momentum P to be equal to gamma mu, where gamma is the Lorentz factor given by 1 over square root of 1 minus u squared over c squared. M is the mass of the particle, and u is the velocity of the particle. Here we see that c is the speed of light, and that is equal to 3 times 10 to the 8th meters per second. If the particle is initially at rest, so that means t1 is equal to 0, and the velocity is initially along the direction of the force. So therefore, we have the work will be equal to the kinetic energy at a certain time t, and this is equal to the integral of the time derivative of gamma times m times u dot dr. Since by definition, u is the derivative of r with respect to time, so therefore we can rewrite this equation as t equals the derivative of gamma u with respect to time dot u dt, or m integral of u d gamma u integrated from 0 to u. By integration by parts, we obtain the expression t equals gamma mu squared minus m times integral of u du over square root of 1 minus u squared c squared from 0 to u, and this is equal to gamma mu squared plus mc squared times the square root of 1 minus u squared over c squared minus mc squared. This allows us to define the relativistic kinetic energy T, which is equal to gamma mc squared minus mc squared. So using again the definition of the Lorentz factor gamma, we can rewrite this as T equals mc squared times 1 minus u squared over c squared to the negative 1 half minus mc squared. And expanding this expression in a power series, we have T equals mc squared times 1 plus 1 half u squared over c squared plus etc. for the higher order terms minus mc squared. Now, considering the classical case where speeds are very small compared to the speed of light, this allows us to neglect all higher order terms such as u to the fourth over c to the fourth or even higher. T is equal to mc squared plus 1 half mu squared minus c squared, which yields the classical kinetic energy T equals 1 half mu squared. Here we can also look at the term mc squared. And as you know, we call this the rest energy, denoted by E naught, which is one of the most famous equations in physics that tells us that energy and matter are equivalent. So therefore, we can rewrite the relativistic kinetic energy to be equal to gamma mc squared minus E naught. Rewriting this equation, we have E equals T plus E naught. Here we define E to be equal to gamma mc squared, and we call this the total energy of the system. This equation shows that the total energy is defined as the sum of kinetic energy and the rest energy. Of course, if the particle is in a conservative force field, the potential energy U should also be included in the mix. So from these equations, we can relate the momentum of the particle to the total energy and rest energy. You can start with the definition of the relativistic momentum, where P is equal to gamma mu. Squaring both sides, we have P squared equals gamma squared m squared u squared. Multiply both sides with c squared, we have P squared c squared equals gamma squared m squared u squared c squared. Multiplying the right side with 1, or c squared over c squared, we have gamma squared m squared c to the fourth times u squared over c squared. Using the definition of gamma, this is now rewritten as gamma squared m squared c to the fourth times 1 minus 1 over gamma squared. Simplifying this, we have gamma squared m squared c to the fourth minus m squared c to the fourth, or gamma mc squared squared minus mc squared squared. Hence, p squared c squared is now equal to E squared minus E naught squared, where E is the total energy of the system and E naught is the rest energy. Rearranging this, we have E squared equals P squared C squared plus E naught squared. So this equation is now the relationship between the total energy E, momentum P, and rest energy E naught. So for instance, a photon, which is the particle of light, is considered to be a massless particle. So therefore, its rest energy should be equal to 0. Hence, the energy of a photon, which is traveling at the speed of light, is given by E equals Pc. This physically means that photon is never at rest. It's always moving at the speed of light. So that's it. That's a short discussion about energy in relativity. And we're going to use these equations to determine the Lagrangian of a particle whose speeds approach the speed of light. So for now, thank you for watching. I hope you learned something today, and I will see you guys in the next video. Bye bye.